Hello, hello everyone. Today we will be seeing some applications of intermediate value theorem. These are very small applications, but they're easy to prove, but they have quite important consequences. So let me start with the first typical application. So let J, which is subset of R, be an interval. Okay, so J is some interval. Further, let f be a function defined from J to R and let it be continuous. So f is a continuous function with domain J and it's a real valued function, and fx is not equal to 0 for any x in J. Okay, so function takes all non-zero values only. Then f is either greater than 0 on J or f is less than 0 on J. Okay, so it cannot take positive and negative values. Either it takes all positive values only or all negative values only. Okay, you can easily see this because see what will happen. We have said in the intermediate value theorem that if a function takes two values, so for example, f takes one negative value and one positive value at least, then it must take value 0 somewhere. Okay, even if it is like this, intermediate value theorem says that it should take every value in between. Okay, so let us write the formal proof and we will prove by contradiction. So suppose the result is not true. Okay, suppose the result is not true. Therefore, this would mean that there exists x1, x2 in J such that fx1 is less than 0 and fx2 is greater than 0. Okay, there exists 2 points, means because we are saying result is not true. Not true means it doesn't take all positive or all negative values. So there will be at least one point where the value is positive and there will be at least one point where the value is negative. We are calling those points as x1 and x2. And now by intermediate value theorem, there exists C which is between x1 and x2. Depending on whether x1 is small or x2 is small, there exists C between x1 and x2 such that fc is 0, because intermediate value theorem says that if I have 2 points where one is taking positive function value and another is taking negative function value, then in between 0 should be attained. And this is a contradiction because we have been given that the function doesn't take 0 value on its domain. So the result has to be true. Okay, let me go to second application. Now suppose f going from R to R be a continuous function taking values in Z or Q. Okay, taking values in Z or Q, then f must be a constant function. Then f is a constant function. Okay, now see, we are saying f is continuous and we are saying that it takes values only in Z or Q. What do we know about Z? That values in Z are like this. In between there is a gap. Okay, and we are saying that f takes only values in Z. So if f is continuous, then by intermediate value theorem, if a function takes say this value and this value, so at least two distinct integer values, then all the in between values must also be taken by it. But we are saying that it doesn't take in between values. So f must be continuous. F must be constant, that is it should take only one value. It cannot have two distinct values. Okay, let us try to write a formal proof. So again we will try by contradiction. So suppose f is not a constant function. Okay, suppose f is not a constant function. This implies that f takes at least two distinct values. Not a constant means it takes at least two distinct values. So there exists x1, x2 in, I will prove for q, but the proof for z is exactly similar. There exists x1, x2 in q such that um, f of some point, so f of, there exists x1, x2 in q such that x1, x2 belong to range set of f. Okay, range of f. Okay, this would imply, by intermediate value theorem, this would imply that there exists C such that every in between value is taken. Okay, now where the problem is, we are saying that f takes values only in q, so f cannot take irrational values. Okay, but by density of irrationals, by density of irrationals, there exists point r belonging to q complement such that x1 is less than r is less than x2, because x1, x2 are anyway rationals. Okay, there exists an irrational number r such that r is between x1, x2, and then by intermediate value theorem, there exists some c in r such that f of c is equal to r, because r is an intermediate value. X1 is one possible value of f and x2 is another possible value of f. So r is an intermediate value. So it must be taken. But this is a contradiction because we are saying that f takes values only in q. It doesn't take values in irrationals. So f cannot take two distinct values and hence f must be a constant function. Okay, this is a contradiction. Therefore, f must be a constant function. This is another application of intermediate value theorem. Okay. Now let me talk about third application. It is also pretty simple. So third application says if f from AB to R is a non-constant continuous function, f from AB to R be a non-constant continuous function, then f of AB must be uncountable. F of AB must be uncountable. Can you see the proof? Again, we are saying that it is a non-constant function. So it takes at least two distinct values. Okay. So f is non-constant implies f takes at least two distinct values. Okay. Two distinct values, say y1 and y2. Now by intermediate value theorem, every value between y1 and y2 is taken by some point. By intermediate value theorem, the interval y1, y2 becomes subset of range set of f. Correct? Because intermediate value theorem says that if you take any point between y1 and y2, then that point corresponds to, that point is an image of some point. Okay, so y1, y2 entire interval becomes subset, and we know every interval in R is uncountable. Okay, we will say here without loss of generality, y1 is less than y2. Okay, every interval we know is uncountable. So range set of f is superset of an uncountable set and hence it must be uncountable. Okay. So these are implications of intermediate value theorem. Uh, as another consequence of intermediate value theorem, we have what is called as fixed point theorem. Okay. So let me now state and prove that. Fixed point theorem. So what is a fixed point theorem? Let me give statement. So let f from AB to AB be a continuous function. So the domain as well as the range are same. Be a continuous function. Then there exists C in AB such that FC is equal to C. So such a thing is called as fixed point. So C is a fixed point of f. Fixed point of f means the function f does not move C. In that sense, C is a fixed point. Okay, the function f maps C to itself. Okay, so C doesn't move under this function. So this C is actually called as fixed point of a function. Hence the name of the theorem is fixed point theorem. Okay, so what we will do? We will define gx as fx minus x. So what will be GA? GA will be FA minus A. What I know is FA belongs to AB. So FA minus A has to be always greater than or equal to 0. Similarly, GB will be FB minus B. And what I know is FB also belongs to AB because the the range is also AB. So FB has to be less than or equal to B. So this is less than or equal to 0. Therefore, by intermediate value theorem, there exists C in AB such that G of C is equal to 0. G of C is 0 means f of C minus C is equal to 0 and hence f of C is equal to C. I think I might have mentioned this in the introductory lecture or in the orientation lecture that actually it is very easy to visualize proof of this via graph. So suppose I have A and B here and then corresponding A and B here, okay, the function values. Then we are saying that if a function lies in between this, then it must cross this line at least once. Okay, the line, straight line. Okay, so this I will erase because this is not the line. Okay, so this is not what I want. Yeah. So this straight line x equal to y, this straight line will be crossed at least once by any continuous function that you draw in this range. See, you can draw any function, it will always cross this straight line somewhere. Okay, or at least at the end points, if not in between. Okay, so this is fixed point theorem. Um, there are two more implications of these results which we are going to need every now and then. One of them is called as extreme value theorem. Okay, what is an extreme value theorem? So it says that if I have a function which is defined on a closed and bounded interval, and if the function is continuous, then the function must be bounded. Okay, and it further says that the bounds will be attained. Okay, so let me first write the bounded part of the statement. So this is also actual extreme value theorem. Let me write first. So this is, so let f defined from AB to R be a continuous function. F defined from AB to R be a continuous function. Then there exists there exists x1, x2 in AB such that fx1 is less than or equal to fx is less than or equal to fx2 for all x in AB. So we are saying two things in this. So we are saying that fx is always between these 2 points, means we are saying that f is bounded, and we are further saying that these bounds are actually attained. Attained means fx1 means you can always uh, say that this continuous function defined on a closed and bounded interval will attain its LUB and GLB. Okay, so you will have points which give you that bound. Okay, so how do you prove that? So I won't discuss the complete details of the proof, but we will discuss the idea, and then it should be easy for you to understand. So first let's discuss the bounded part, that is known as Weierstrass theorem. So Weierstrass theorem simply says that the function is bounded. It doesn't say that the bounds are attained. Okay. So how do I prove that the function is bounded? So it uses the nested interval theorem. So this is an interval AB. If the function is not bounded on this interval, then it is not bounded on at least this half or this half, one of the two halves. Because if it is bounded here by some bound say m1, and if it is bounded here by some another bound say m2, then I can define m as maximum of m1 m2, and then it will be bounded on entire interval. Okay, so at least one of these two intervals has function value unbounded. Okay, then we will further divide this, and we'll keep on doing this until finally we have reached a point where there is a unique point in the intersection. Okay, so there exists some C which is in intersection of these intervals, all these unbounded intervals, and C is a unique point because the interval length is decreasing, right? So we have seen earlier, because the interval length is decreasing, at the end there will be at most one point in the intersection, and we already know that point, because of our local boundedness thing, we can have an interval c minus delta to c plus delta which is outside the interval, which covers the interval, and in this interval the function is bounded. So this is contradiction to the fact that the function is unbounded in between. Okay, let me try to write the formal proof. So suppose the function is not bounded on AB. This implies there exists at least one interval out of a to a plus b by 2 and a plus b by 2 to b such that the function is not bounded on this interval. The function is not bounded on this interval. Okay, function is not bounded on this interval. We keep on dividing this interval further. Such that J1 is superset of J2 is superset of, and so on, and function is not bounded on any Ji. Function is not bounded on any Ji because we are always picking that half where function is not bounded, and length of Ji is b minus a upon 2 raised to I. Okay, therefore by earlier results which we have proved, there exists C in intersection of Ji. Further, since the function is continuous, there exists delta greater than 0 such that function is locally bounded in c minus delta to c plus delta. We have shown this earlier. Okay, so this would imply, but length of ji is going to 0 because it is b minus a upon 2 raised to I. Therefore, there exists n naught such that jn naught is subset of c minus delta to c plus delta, because c minus delta to c plus delta has length 2 delta. So I can choose an interval which has length less than 2 delta because length is anyway going to 0. Okay, so this would imply function is bounded on jn naught. Okay, this would imply function is bounded on jn naught. And that is a contradiction because we already said function is not bounded on any ji. Okay, therefore function must be bounded on entire AB. Okay, function must be bounded on entire AB. Okay, so this is a proof of the bounded part. And for the part where we have to say that the function is the function attains its extreme values, let me go to that part. So how do I prove that part? So we will define M as LUB of the function values. Okay, so M is actually LUB of the range set. So M is LUB of set of all fx such that a is less than or equal to x is less than or equal to b. Okay, so we want to prove that this M is attained, means this M is actually fx for some x. Okay, now suppose it doesn't happen. So suppose M is not equal to fx for any x. Okay, M is not equal to fx for any x. So what would it mean? It would mean that M minus fx is greater than 0 on entire interval AB, because M is an upper bound. M is always larger than fx, and we are saying that M is not equal to fx for any x. So M minus fx is greater than 0 for every x in AB. Okay, and fx is continuous. So this would imply M minus fx is also continuous. Fx is continuous, so M minus fx is also continuous. As a result, if I define g as 1 upon M minus fx, then what happens? Then g is still continuous. I can define this g because M minus fx is positive. If M minus fx took value 0, then I cannot define this g. But right now it is taking only positive values, so I can define this d, and this g is continuous. We have already proved that if f is continuous and if it takes non-zero values, then 1 by f is also continuous. Okay, so g, which is 1 upon M minus fx, this is also continuous. Okay, and what I know is that this g is a continuous function defined on closed and bounded interval. Hence, by the above part which we proved, g must be bounded. We have proved the part. So g is bounded. Okay. So bounded means bounded above as well as bounded below. Okay. So g is bounded above means gx is less than or equal to some a. So there exists some a in R such that gx is less than or equal to a for every x. This would imply 1 upon M minus fx is less than or equal to a for every x in AB. Okay, we have used the first half of this. Okay, so this would imply m minus fx is greater than or equal to 1 by a for every x in AB. Okay, this would imply m minus 1 by a is greater than or equal to fx for every x in AB. So this would mean that m minus 1 by a now becomes an upper bound for fx. Okay, because it is larger than or equal to fx for every x in AB. But just now we proved that, just now we defined m as the least upper bound, and m minus 1 by a is smaller because we said g is positive and hence a is positive. So m minus 1 by a is smaller than m, and that becomes now an upper bound, which is a contradiction. Okay, so this is a contradiction to the fact that m is LUB. So m must be equal to fx for some x. Okay, and same story you can repeat by defining small m as GLB. Okay, so that part I'm leaving as homework for you. So right now what we have proved is upper bound is attained. Now you have to prove lower bound is attained. For that you have to define GLB and then argue exactly similarly. Okay, so m minus fx will be always taking negative values, and then you again defining the same way. Okay, so let me stop here. Thank you.